never changes. If the speed doesn't change, then the velocity, of course, does change, because the direction changes all the time. But the speed does not. So here we have our circle. Let this be radius r. And at this moment in time, the object is here, has a certain velocity. This is 90 degrees. And at later in time, the object is here. The speed is the same, but the direction has changed, 90 degrees. So these vectors should have the same length. In a situation like this, that we have uniform circular motion, so it's uniform, circular motion, we first identify what we call the period, t, in seconds. That's the time to go around. Then we identify what we call the frequency. That is how many times it goes around per second. I prefer the letter f, but our book uses the Greek letter nu. I find the nu often very confusing with the v of velocity, and that's why I prefer the f. It is 1 over t, and so the units are second minus 1, but most physicists would call that hertz. 10 hertz means to go 10 times around per second. And then we identify omega, the angular velocity, omega, which is in radians per second. Since it takes t seconds to go around 2 pi radians, omega is 2 pi divided by t. Now then we have the speed, which we can also think of as a linear velocity. How many meters per second is linear as opposed to how many radians per second, which is angular velocity. So this is a linear velocity, this is an angular velocity. And that linear velocity, which in this case is really a speed, is of course the circumference of the circle divided by how many seconds it takes to go around. And that is also omega r. And that is now in meters per second. All this is only possible if there is an acceleration. And the acceleration is called the centripetal acceleration. It is always pointed towards the center, A centripetal, A centripetal. And the centripetal acceleration, the magnitude, is v squared divided by r, which is therefore also omega squared, and that of course is in meters per second square. I want to work out a specific example, and the example that I have chosen is the human centrifuge that is used by NASA in Houston for experiments on humans to see how they deal with strong accelerations. This is that centrifuge. The radius from the axis of rotation, the axis of rotation is here, and the distance from here to here, though you may not think so, is about 15 meters. So the astronauts go in here, and then the thing goes around. And so I would like to work out this with some numbers. The radius r, I'll give you light back, because it may be nicer for you. The radius is 15 meters. Depends, of course, a little bit on where the person is located in that sphere. It goes around 24 revolutions per minute. And that translates into 0.4 hertz. So the period to go around for one rotation is 2.5 seconds. The thing goes around once in 2.5 seconds. So the angular velocity omega, which is 2 pi divided by t, if you take 2 pi and divide it by 2.5, it just comes out to be roughly 2.5, which is purely accident. That's the way it is. Don't ever think that that has to be the same, of course. It just happens to come out that way for these dimensions. So omega is about 2.5 radians per second. And the speed, the linear speed, tangential speed, if you want to call it, is omega r. That comes out to be about 37.7 meters per second. And that translates into about 85 miles per hour. So it's a sizable speed. What, of course, the goal is for NASA, what is the centripetal acceleration? That is omega squared. Or if you prefer to take v squared divided by r, you'll find, of course, exactly the same answer if you haven't made a slip, and that is 95 meters per second squared. And that is about 10 times the gravitational acceleration on Earth, which is really phenomenal. If you add to the fact that the direction is changing all the time when you go around, so you feel the 10g in this direction, and then you feel it in a different direction. I can't imagine how people can actually survive that. I mean, not faint. Most people like you and me, if we were to be accelerated along a straight line, not even a circle where the direction changes, but along a straight line, most of us faint when we get close to 6g. And there is a reason for that. You get problems with your blood circulation, and not enough oxygen goes to your brains, and that's why you faint. How these astronauts can do it at 10g and the direction changing all the time, it beats me. If you take a Boeing 747, it takes 30 seconds from the moment that it starts on the runway until it takes off. You should time that when you get a chance. It's very close to 30 seconds. And by that time, the plane has reached a speed of about 150 miles per hour. And if you calculate, if you assume that the acceleration is constant, it's an easy calculation, it turns out that the acceleration is only 2 meters per second squared. That is only 1/5 of the gravitational acceleration. It feels sort of good, right? It's very comfortable when you're sort of taking off, and it's only 2 meters per second squared. These poor people, men and women, 95 meters per second squared. I would like to address something that is not part of the exam, but that is something that I want you to think about, something that is fun. And it's always nice to do something that is fun. It has to do with my last lecture. I have to clean my hands first for it to work quite well. I have a yardstick here, and I'm going to put the yardstick on my hands, on my 2 fingers, which I hold in front of me. Here it is. It's resting on my 2 fingers. And I'm going to move my 2 fingers towards each other. One of them begins to slide first, of course. I can't tell you which one. But something very strange will happen. If this one starts to slide first, it comes to a stop, and then the other one starts to slide, and it comes to a stop, and then this one starts to slide, and so on. And that is very strange. This is something you should be able to explain, certainly after the lecture we had last time. Look at this. Did you see the alternation? I'll do it a little faster. Left is going, right is going, left is going, right is going, left is going. Once more. Look at it. Left is going, right is going, left is going, right is going. They alternate. Give this some thought. And you know, Pivot has an option that you can discuss problems with other students. So make use of this discussion button and see whether you can come to an explanation. Good luck on your exam. See you next Friday.